We know that vectors can have different magnitudes, but if we can assign a magnitude of 1, this will be helpful in defining different vectors in different formats. So we will start with a basic definition of a unit vector, but next lesson we'll cover the unit vector in depth. So unit vectors are any vectors that have a magnitude of 1. So this is very important, as it's going to establish the basics to writing vectors in a different form. We will start with what we call the base unit vectors. So these are unit vectors that we will continuously use to represent our vectors. So the base unit vectors are I and j, which is another fancy way of saying how many units your vector is moving to on the x-axis and how many units in the y-axis, assuming that I is your vector moving only 1 unit in the positive x-axis. So if this is my axis here, then this is I, just from the center to one position, and then j will just be the vertical going in the positive y-axis direction. So the I and j are universal letters we use to represent the base unit vectors, and I can say that I is just 1 times I and 0 of j, and I can write it in this column format, and j would be as such, but for the y values. So this is not an unusual format. You should have seen this type of notation before, but now we're just building up the definition. So these are unit vectors. They have a magnitude of 1, and they represent the base unit vectors. So based on this, I can write in 2D, I can write all my vectors as a linear combination of this I and j. So I can write it instead of having it written in position vector or just a free vector, I can represent them using component or algebraic form. So we call them both either component form or algebraic form. You need to know the names just in case questions ask you for a specific form. So this is where you are writing each component separately. So the I and the j. So 3, if you look at here, this is point A or vector A, and I'm moving 3 units to the right. So 3 i's, and I'm moving 2 j's up. I can also write it as in column form, so where this represents how much you're moving in the positive x direction and positive y direction, and or how many i's and j's you're moving. So based on that, I can refine my definition of position vector. So position vectors are vectors that start from the origin and go to your point. So this is where x and y are useful. So you've seen this notation before again, but we're just reinforcing it and applying it to vectors. So based on these definitions, we can continue with basic operations. So the same operations we've dealt with before, how can we apply them to the component forms or column form? So let's say I have vector A with these coefficients for I and j, and vector B with these coefficients. So if I want to define equality, so we're just going to define the basic operations like we did before. Equality implies that vector A equals vector B, and this implies that the I components would be equal and the j components would be equal. So you have this. So this is the symbol for if and only if. So if these are equal, then it implies that the components are equal, or if you see the components are equal, then the two vectors are equal. Then we have the addition definition. So if I'm adding two vectors, what you end up doing is actually just adding the like component. So again, not very unusual algebraic operation. So I will add the I components together and the j components together. Obviously, don't confuse the I here for imaginary number. In order to distinguish between them, this is where it's very important in writing to either write the I as a bold letter when it's typed, or with a line underneath when you're writing on paper. So this is not the imaginary I, it's just the unit vector I. In column form, you can see you can just add the top values which represent the coefficients of the I component, and the bottom value which represent the coefficients of the j component. Scalar multiplication, it spreads throughout, so if it expands out, you can distribute it, so the scalar will multiply to each of the components. So it will multiply with the I component and the j component. Similarly here in column form, you can either keep it out or write it inside. We do both. And finally, in linear combination, I can multiply by different scalars with different vectors. So as you can see, I am multiplying, I'm doing a couple of operations. First, I am multiplying. So you can see that I'm multiplying the scalar alpha for my vector A, but then I'm also adding it to the vector B as well. So just individually doing the operations, you can see it maybe much clearly in column form. I am multiplying by scalar A, so I'm multiplying the vector A by the scalar lambda, and I'm multiplying the vector B by a scalar mu, and then I need to add the components together. So I'm adding the coefficients of the I component and the j component. So this is just to emphasize how all of these operations work with column vectors. Again, not very unusual. Just a note on subtraction, so this is something we'll use, a notation we'll use. When subtracting vectors, we tend to write them in order of terminal point minus initial point. So if I want to move from A to B, I know that the operation is A to O and then O to B, which is basically a negative A plus B, but we tend to write it as B minus A. So we will tend to use this notation quite often. So, or we sometimes say AB is OB minus OA. So very common to represent it in this way. Remember that they are commutative. I know that technically we are moving a negative, so this is negative OA. If you think of AO, it's the same thing as negative OA plus OB, and vectors are commutative, so I can swap these around and it will give me the same thing. So by convention, we tend to write the subtraction in this format. So we'll go through a couple of examples. These are easy to do on your own, but you can pause the video and try them, or you can listen to the explanation. So we can do some of these basic operations. You can, since the question didn't specify, you can leave them in component form or in column form. I'll do both, but I like column form because it's just easier to write. So for part A, I'm just adding the two vectors. I know this is 3 and minus 2, and I'm adding minus 1 and 4, and adding them together will give me a 2 and 2 vector. So you can leave it in column form, or you can write it in component form as well, depending on what the question wants. And then for parts B, you're multiplying by a scalar, so 3 and minus 2, so that gives you the 9 minus 6. For C, you're multiplying, and you are multiplying by a negative, so be careful with the signs. You end up with a 2 and minus 8. And then for part D, we're doing a linear combination. So I'm doing, this time let's just make it a bit different. Let's do it in component form. Just to show you something different. So minus I for j, and I'm gonna multiply each of the components. So I give the 15i minus 10j, and then I'll multiply here as well. So I get minus 4i plus 16j. And then just like you do with algebraic operations, you just combine the like terms. But in this case, we don't call them like terms. It's just the fact that they are components. So it doesn't make sense to add a j and an I because they represent different directions. So you take the similar components, and we end up with this. And then a slightly different question. This time I want to express a given vector as a linear combination of these two others. It might not be very obvious what linear combination to use. Trial and error is not recommended as it will take a long time depending on the route you're taking. But let's just set it up for now. I know that I want C to be equal to something with A and something with B. So let's set it up. So I have 4 and minus 7, and I want it to be equal to something with minus 1, 1, that's the A vector, and a 2, minus 3, that's the B vector. So hopefully you can spot that you'll have a simultaneous equation, and you're looking for, since the components are separate from each other, you are looking for this to be equal, and then you're looking for this to be equal. So you set up your simultaneous equation. You get a negative lambda plus 2 mu is equal to 4. I'm just shifting the C to the other side. And then you have a lambda minus 3 mu is equal to minus 7. So you have a simultaneous equation. I'm not going to go through that process. You can then see that your lambda is going to be equal to 2, and your mu is going to be equal to 3. And you can check as well, so just to make sure it works. So vector C is now, don't stop there, make sure you answer the full question. Vector C is going to be 2 it's going to be 2 of vector A plus 3 of vector B. And again, check that you have this correct combination, and actually gives you vector C. Let's see what direction vectors. The next 2 worked examples are going to be quite interesting to look into. The way we're gonna, you'd know how to solve these if it was on a graph paper and you're looking at the values and you can easily see how it works. But the idea of the next 2 questions is how can we use vectors to prove and find these values. So again, the idea is to use vectors in this case. You can do a rough sketch of what these points are gonna look like. Remember that these are points, these are not vectors. I haven't written them in position vector yet or direction vector, so just keep that in mind. These are points, so you can roughly kind of tell it's going to be something. You have a parallelogram as such. There are different ways to solve this question. I'm going to do it one method, and you can attempt a different method as well. Now I need the coordinate of point C, and we will need the lesson from geometry to be able to solve this type of question. Well, I know A, D, and B. I know the positions, their points, but I don't know C. But I do know something else. I know I can figure out the distance, or not the distance, the vector that gets you from A to D, and I know that it's going to be parallel to the vector that takes you from B to C. So if I can find A to D, I can apply it to B and C. So that's the idea behind this question. So before we start, we first need to figure out what A to D is, and this will be as we've mentioned before on the notes on subtraction, this is going to be O to D minus O to A. Alright, so if you're still confused about this, go back a few minutes ago where I explained it on the notes on how we write subtraction. So to do this, I know O to D. So these are points, these are from the origin. So we know O to D is 0, 2, and I'm taking away minus 2, minus 1. So that will give me a 2 and 3. So I know that AD is 2, 3, or you can write it in component form, 2i plus 3j. So this is 2i plus 3j. And I know that this should also move a 2i plus 3j, but from a very specific starting point, which is B. So I know BC should also give me 2, 3. I also know that BC is basically OB minus is OC minus OB. And let's replace some of these values. So I don't know what OC is. That's what we're trying to find. That's the question. And I'm taking away OB, which is 3, 0. And then moving things around, you have 2, 3, and you're adding 3, 0. This will give you OC that we need, which is 5 and 3. So I 3j. So that's the components, but we know as a vector the point C will have coordinate 5, 3. So we can apply the same idea to 3D space as well. So far we've been dealing with 2D. In 3D we just add an additional axis. So in 2D we have the x and y, and when we go to 3D we add that additional direction, which is the z axis. So we also define a unit vector for the z axis, which is a k. So now we have the 3 base unit vectors, I, j, and k, and a linear combination of I, j, and k will give you any vector in 3D. So the operations are obviously going to apply the same way. It's just that you're dealing with 3 components. So for this question, we're going to set it up just like the previous question. We're looking at, but this time A is the origin. You can see it has a 0, 0, 0. So the idea is to look at a specific distance that will get you to C, and then something similar to C. So if you look here, I can figure out the value from A to B. So that will give me the how much am I moving from A to B, and then apply that similarly from D to C as they would be parallel. So that's for part A. A to B is basically OB minus OA. which is kind of silly to write, but let's just write it down. O to B is 2, 3, and 0. And I'm taking away O to A, which is just taking away 0. So a bit redundant, but let's just keep it there. And then I know that this represents the vector movement here, and I know it's parallel here. So precisely from, I know D to C will have the same sort of movement. And I know that it should be equal to 2, 3, 0 because they are parallel. O to C, I don't know what that is. That's what I'm trying to find. O to D, I have that as -1, 4, and -2. And I can immediately move it to the other side. O to D would be -1, 4, -2. And when I simplify, I get the following. So the coordinate C is going to be 1, 7, -2. As a coordinate, because it's coordinates, you don't write the components I, J, and K. And then part B, we do something similar, but for G, you can see it's a movement here. So if I can look at A to E, I can then apply it to C to G. So A to E would be OE minus OA. Similar to the beginning step, it will just give you 1, -2, and 6. And then C to G is basically OG minus OC. And it should be equal to 1, -2, and 6. But I know, we know OC now from the previous question. So OG is equal to 1, -2, 6, plus 1, 7, and -2. And that will give us 2, 5, and 4. You can solve this differently. There are different ways to approach this, different vectors, different positions. You can do a combination of A, B, and C, and so on. But this is just one method to go about this.